So the first part of the, what we just talked about is, and I guess it's a necessary evil, but really, this is the first calculational technique. I mean, okay, separation of variables we did over there, right? But now I'm really getting to the sort of meat and potatoes of the course. So this is how to solve first order differential equations. Now, a purist mathematically might want to talk to you about the existence and uniqueness theorems of differential equations before that. But in my experience, I think students probably understand existence and uniqueness theorems better once they've seen a few equations solved. And so that's what we'll talk about at the end of today, like the last 20 minutes or so probably. I'll spend showing you the existence and uniqueness theorems and something called direction fields and all that. That's what I would generally speak of as more qualitative methods, ways of visualizing solutions without actually finding a quantitative formula for them, right? So what we're involved in right now is how to find quantitative, explicit, or implicit general or possibly initial value solutions to differential equations. So a first order differential equation, generically speaking, looks like this. So we're gonna use y and x as our, because that's what you're familiar with, and so generically speaking, something like this is a first order differential equation, all right? So this is what we want to solve, how to solve this, right? And there are three main methods, I would say. Separation of variables. We already saw one of those, all right? The other method is the integrating factor technique. All right. I can't spell. And then the other, of course, is the technique of exact equations. These are not mutually exclusive. And, oh, fine. I mean, I guess I say there are three, but I always feel obligated to say, all right, fine, there's also substitutions. But to me, substitutions is kind of a, I don't know, it's a little bit more out there. What's in blue, these are the main methods, right? These are my go-to methods. They're not mutually exclusive. There is some overlap. So let's just get to it. If we try to solve dy dx equals to, let's say, x over y, and let's say y of 0 is minus 2. Let's try to solve this. So the question is, what method can I use? Well, separation of variables is going to work good here, because when I go to separate the variables, I can do it, basically, So dy dy equal to x dx. If you can do that, if you can put all the stuff with x on one side and all the stuff with y on the other side, then the equation is said to be separable, right? If you want me to be more sort of technical about it, a separable differential equation allows this to be rewritten as like f1 of x times, say, f2 of y or something like that, all right? You can find separate functions, f1 and f2, such that one is just a function of x and one is just a function of y. So you could rewrite it multiplicatively as a product of functions of x and y. If you can do that, separation of variables will work for you. All right, so same usual song and dance, integrate both sides. This gives us 1/2 y squared, 1/2 x squared, plus a constant, right? And I guess I should, since we're starting, I should be a little more careful. This is the problem. What's our goal? Find explicit solution to the initial value problem. All right. That is an initial value problem. So what I've found is a solution, right? I found the implicit general solution at this point. but that's not the end of the story, right? You notice I haven't used the initial condition yet. So what's my next move here? I'm going to solve for y, actually, if that's okay with you guys. So y squared is equal to x squared plus 2 times the constant, right? And then y is equal to plus or minus the square root of x squared plus 2c. Now, if you're looking for an explicit solution, all right, that means you're looking for a single function which solves the differential equation, right? Or class of, and the initial condition, or a class of functions, right? If it's an initial value problem, you can't have plus or minus in the solution, right? I mean, you have to choose a plus or a minus. The answer should be one function. On the final exam I just gave in the last semester, I had 30–40% of the class put plus minus in this kind of problem, and that's wrong. Because you have to address the issue. Do you choose plus or minus, right? I want y of 0 to be minus 2. Can I get minus 2 from plus the square root? I cannot. It's not simply not possible. This has to be minus the square root of 0 squared plus 2c, right? So that once you have the, I mean, this says we must choose the minus of the plus minus possibilities, all right? And past that, it's just algebra. Square both sides. We get 4 is equal to 2c. So therefore, c is equal to 2. And so what we get is y is equal to minus the square root of x squared plus 4. There we go. Does that make sense? All right. Let's see here. I'll try to work out some of the examples in the notes together. Partly because they're usually good examples. Partly because I want to find errors. All right. Here we have dy dx equals to minus x over y. Find implicit. Well, let's just say find solution. Now here I'm not telling you, I said find solution, right? So implicit solution will work. This red is a little bit hard to see in this room. Sorry about that. I will stop doing that. All right, so is this separable? Yes. Separate variables. We get y. Oh man, this marker again. Sorry, I got to go up. Next break, I'm going to go upstairs and get some better markers. Y dy equals minus x dx. Separate, integrate. We get 1/2 y squared minus 1/2 x squared plus a constant, right? Now, I could just put a box around that. There you go. Answer, done. Hooray. But it's also nice to rewrite this answer in a little bit more sort of geometrically lucid fashion. And so what I would do here is I would rewrite this as what? This is really x squared plus y squared equals to what? Well, 2c, right? But I think a better thing to call twice the constant is what? Maybe, how about just r squared, right? Because the solutions here are what, geometrically? What is the solution set of that equation, x squared plus y squared equals to r squared? Yeah, circles, right? You guys know this. So the solution set, I could even draw it, right? Now, to be picky, I suppose the solutions to this differential equation don't technically exist here and 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 here, right? Because That's where y equals to 0. You've got division by 0 there. Technically speaking, the differential equation's not really defined there, is it? So what would be a way we could write the differential equation such that I could throw those points back in? Is there a notation that would not make y special in that regard? Let me just pause here. Do you guys understand how we solve this? Fine? Good? Do you understand why I'm saying, technically speaking, these points are omitted from the solution? Right? I mean, there's vertical tangents, right? So you try to write y as a function of x at those vertical tangents, you can't do it, right? Now, if instead of looking at this like this, if we trade this for y dy equals to minus x dx, or better yet, x dx plus y dy equals to 0, then this differential equation is what's called Pfaffian form. Pfaffian form doesn't make x or y special. It writes a differential equation is actually an equation involving differentials, right? It's a nice notation. It doesn't take x or y as special. And this differential equation meaningfully has the whole circle as solutions, every one of them. Okay. So one of our goals today is to understand the Pfaffian form and how you deal with it. One answer to that question is, well, you just separate variables just like we just did. I mean, if this is your starting point, you could still take the starting point and do that, right? And go through this, and you'd find the solution. You'd find the solutions, except, well, actually, this doesn't have a problem with with y equal to 0, does it? That's the funny thing, right? Your solution seems to have added in points which were apparently not defined in the differential equation. Yeah. This is not really a new thing, though. I mean, this sort of thing happened in algebra too, right? Sometimes you do some sort of solution technique, and you end up adding points to your solution set through the technique, right? Like when you square an equation, you may erase a minus and add an extra solution, so forth, things like that. Okay, another example. Let me not talk too much about these. You guys don't usually have trouble with these, right? Here's a good one. Example 3, let's try to solve dy dx equal to e to the x plus 2 times the natural log of the absolute value of y. All right? Find explicit solution. All right, so at first glance, it doesn't look separable, right? Because it doesn't look like we've got a product of function of x and function of y. So what's in our way here? An algebra step, right? So we need to know that e to the x plus 2 natural log the absolute value of y is what? It's equal to e to the x times e to the 2 natural log the absolute value of y, right? Properties of exponents. How about 2 times the natural log of the absolute value of y? Does that simplify in any way? Can we simplify that? We can pull the 2 inside, right? The properties of logs. That's 2 times the natural log of the absolute value of y squared. What's the absolute value of y squared? Do you guys remember what the absolute value of y is? Well, it's plus or minus y, right? I mean, so when you square that, what happens to the plus or minus? It's gone, right? So it's just what? This is just the natural log of y squared, right? If you guys are all shaky on properties of exponents and logs, you should review, right? Because you got to be precise. You got to know exactly what you're doing. If you don't have those tools in your toolkit, it will really hurt you here. Anyway, so what is this? This is e to the x times, that's just y squared, right? So you see, after a little algebra, our differential equation is actually dy dx equal to e to the x times y squared, which is quite clearly separable, right? And so we separate variables. We integrate. I think we can do that. Let's see here. So we got dy over y squared equals to e to the x dx. Integrate both sides. We get what? Minus 1 over y. Man, I'm sorry. I did this example like this before, right? I'll look in the book and try to find something more awful for us to do here in a second. So integrating gives me that, and then I reciprocate to solve for y, right? Y equals to minus 1 over e to the x plus c. There you go. There's the explicit general solution. Something I should point out, something you should have noticed, or should be in the process of noticing, is that this is not quite the same as what you had been doing in, like, Calc 2 or, let's see here. Yeah, well, Calculus 2, really. So you guys remember, what's the story look like in Calculus 2 or Calculus 1? Just think about that for a second. What was the main problem of integration? Aw, man. Ah, dropped. Integration, that's better. So if we're trying to integrate, you know, what do we want? Say f of x dx, right? If you want this to be equal to y, what does that actually mean? I mean, how can you check your answer when you're integrating? You need dy dx equal to what? For example, integral. Did I write dy? I'm sorry, guys, I meant x. So like integral of secant squared x dx equals to tangent of x plus a constant. Why is this true? Because d dx of tangent is what? Secant squared of x, right? So if you look at it, every time we integrate, we're really solving a differential equation. We're solving the differential equation dy dx equals to f of x, right? It's just kind of a boring differential equation. But integration is solving a differential equation, right? Or from another perspective, when we solve differential equations, we're really learning new integration techniques. This course is really more an outgrowth of Calculus 2 than Calculus 3, truth be told. Right? Just a comment. But the other thing I wanted you to notice here is the way the constant appears here is how? Additively, right? Like that. The antiderivative plus a constant. Is it ever not the case that you just add a constant when you're integrating? As far as I can remember, no. It's always additive. But when is it additive? When is the constant additive for differential equations? Goodness gracious. Not really. Like, yeah, we added a constant, but this is not an explicit solution, right? If I find the explicit solution, what's it look like? Y equals to like 2c minus x squared, square root of that, plus or minus, right? And to choose the plus or the minus, I need to figure out whether I'm above or below the x-axis for the solution I'm looking at, right? It takes two functions to glue together to give a circle. So does that constant appear additively? No, certainly not, right? And the solutions also don't look like antiderivatives. How are antiderivatives related? by vertical shifts, right? They're just the same shape shifted up and down. The possible shape of solutions to differential equations is much more exciting. Over here, the constant does not appear additively. It appears down here. So where do you put the constant? How do you know where to put the constant in solution to the differential equation? Where is it? I can't give you a universal answer. The answer is you add the constant when you integrate, and then the constant goes where the algebra puts it. You can't wait till the end to add the constant. If you do, you're wrong. 99.9% of the time here. Unless it's this problem, adding the constant at the end isn't going to work for you. Okay, so I'm giving you kind of not that surprising advice, which is do what I do. All right. Let's see here. So in your book, right? This one's a little wrinkly. Where are we? Separable equations. Formal justification of the method. No one wants to see that. Yeah, let's try to do number 12. That'd probably be good. And then we'll go on to the next method here. I may regret this. Let's see here. Here we have x dv dx equals to 1 minus 4v squared over 3v. All right. And so we're supposed to solve the equation. I guess we could think of v as being the y. But it doesn't really matter. I mean, you could think of x as being the y and v as being the x if you like. The point is we want to try to separate variables, right? Can we do that? Can you separate variables here? I think so. I think this will give me what? This gives me 3v dv over 1 minus 4v squared equals to what? Dx over x? Yeah? Okay, can we integrate now? I mean, we separated variables, right? So what's next? We need to try to integrate both sides. Here we get the natural log, the absolute value of x plus a constant, right? You should ask me a question, right? I mean, like, why do I keep adding the constant to the right-hand side? There's no good reason. It's just a force of habit. I mean, you can add the constant on either side. You could add C1 and C2 on both sides and then combine them later. I mean, it's up to you. I just add the constant on the right side as a force of habit. There's really no good reason for it. It's just habit. Can you integrate this? You should be able to integrate that. We let w equal to 1 minus 4v squared, then dw is minus 8v dv, right? So therefore v dv is minus dw over 8. And so with that substitution, we have the integral of 3v dv over 1 minus 4v squared equals to the integral of 3 times minus dw over 8 divided by w. This is actually a calculus 1 integral. You may have forgotten how to do it, but it's still very much a fair game. Just trying to be honest with you. I'm not trying to be a jerk, but you know, you do need to know how to integrate. Excuse me. So there we get minus 3/8 natural log the absolute value of w plus a constant. Of course, I don't need a constant on both sides. I can just keep one of these constants. I'll call this one C1, call this one C2. Let's put them together. What we get? Minus 3/8 the natural log the absolute value of w, which was what? 1 minus 4v squared is equal to the natural log the absolute value of x plus a constant. Now, of course, that is an implicit general solution to the problem, right? So whether or not we're done depends on the instructions to the problem, right? If I said find the implicit general solution, well, hooray, we're done, right? But let me be a little bit less friendly to us. Find x as function of v. So in other words, now to finish, I have to solve for x. Let's see here. So the way I would do that, I say, okay, so I got natural log the absolute value of x equals to, I don't know, the natural log the absolute value of 1 minus 4v squared to the minus 3/8 power, right, using properties of logarithm. I bring the minus 3/8 into the argument of the exponent. I guess I can subtract the constant like that. Then I just exponentiate both sides. So take the exponential of both sides. What's that give me? So here we have e to the minus c times the absolute value of 1 minus 4v squared to the minus 3/8 equal to the absolute value of x. So let me just make the finishing blow here. Get rid of my circles. All right, so this says that x is equal to plus or minus e to the minus c times the absolute value of 1 minus 4v squared to the minus 3/8 power. Right? So plus or minus a constant, we can just write as, say, k, right? So I'll just call this thing k, and what we have then is x is equal to, I don't know, I just like to write it this way. I mean, it's up to you, but I'm going to write it this way. I just think it's prettier. You're like, well, how do you decide what's prettier? I don't know. Beauty's in the eye of the beholder, I suppose. I mean, I'm married, right? Let's see here. So k over this. It's a comment about me, not my wife. Just to be clear. Let's see here. There it is. Solve for x. What was the hard part? It wasn't the differential equations, was it? If you perceive anything to be hard here, it probably was the algebra I did at the end, right? So, okay. So that's a pretty good few examples on separation of variables. That brings us to our next technique, which is the integrating factor method. Well, can I erase? I'll wait till you guys catch up. Have you guys caught up with me? I'll start erasing over here. Oops. Are we good? Can I finish? Right. see if I can find the marker, which was good. Which one was it? This one? Haha. I really should just throw these all out and start over. So, integrating factor technique. The integrating factor technique is for, it solves linear first order ODEs in form dy dx plus p times y equals to q. So this right here, I'll call star, to give it a name. This is a first order differential equation in so-called standard form. All right? So what I'm going to do here, I'm going to do two things at once. I'm going to give you, on the one hand, example 5. On the other hand, I'm going to give you the general algorithm, because I think it's helpful to see the general algorithm paired with an example. And also, this is, I mean, basically, I'm also showing you a proof of the method, but the proof of the method is the method. So that's why it's worth showing you. Let's see here. So here's a good example. Dy dx plus, I don't know. Tell you what, my examples are too boring. Let me look in the book. There we go. So, oh no, that one's no good. That was not the, come on. I'll do number 1. X squared dy dx plus cosine x equals to y. Is that right? Oh, no. No. The question there is to decide if the problem is linear, separable, or neither. That is very different than saying solve it. See, if I tried to solve this, in about 3 steps, we would find ourselves trying to integrate something like, I guess we could, well, I think the integration doesn't pan out here. So let me try again here. How about number 13? See, that's still not what I want. I'm sorry, guys. I'll get it eventually here. That's still too awful. Dang it. Number 10, maybe. X dy dx plus 2y equals x to the minus 3. X dy dx plus, what did I say? I can't even remember. 3 seconds. Grief. 2y. The problems in the book are fine. They're just not the first problem I wanted to work. That's the thing. Okay. Now, so to start with, that's a kind of a good problem because it doesn't come to us in standard form, right? So like the first thing I need to do is to put it into standard form, which means to get dy dx on its lonesome, right? So this is going to be dy dx plus what? Plus 2 over x times y equals to what? 1 over x to the 4th, right? All right, so now the differential equation at least is in standard form. Okay? Sidebar. Could you know, one of the principal complaints that the faculty have about our current calculus book is, this probably doesn't really apply to you, but if your people come after you in the pipeline, so to speak, the calculus book has all of the problems paired with the specific methods. This does not help you for like Dr. Sprano's test, which does not come with integrate this using this technique. It's just here, integrate, right? Because it's up to you guys to know which method to use, right? If we tell you which method to use on the problems, that's like way easier and not really that interesting. Doesn't teach you the analysis that we're trying to get you to learn. which a lot of it is just recognizing which kind of function you're dealing with. I mean, that's half of what we're trying to teach you. Anyway, so this is bad in the sense that I'm telling you this is an integrating factor method problem, right? So what would you maybe try to do? You might try to separate variables here, right? What would happen if you tried to do that? Let me just tell you, what will happen is you won't be able to do it. Okay, because you got like a 2 over x here, you got a 1 over x to the 4th. If we move all of it to one side, you can factor y out of this, but you can't factor y out of that. There's just no way to rewrite it as a product of a function of x and a function of y. So separation of variables just won't work on this problem, is my point. So we need something new. All right, fine. All right, so the general algorithm, and this is, I mean, it's one of those things in here that just makes, I just have to admit, it's just sneaky. So the integrating factor, which I'll call I, is defined to be the exponential of the integral of p dx. What? Right? But that's what it is. This is the integrating factor. Now, so let me call that step 1. So we need to calculate that. So I exponential of the integral of what's p? P here is 2 over x dx, right? Let me use a less dangerous color. This one might not show up in the video. Let's see here. This is exponential of what? 2 natural log the absolute value of x. I think we've seen this algebra already today, right? And what's that? That's 2 natural log absolute value of x squared. But the absolute value of x squared is just x squared again, right? All right, so step 2. I guess over here I need to notice something. What happens when I differentiate this? So there's really, I can't calculate for an arbitrary p, right? But I can differentiate it and show you something about that. What happens when I differentiate this expression? We get exponential back, right? Then chain rule says differentiate what? The inside function, right? What's the derivative of the antiderivative? Right. It's like you're after class, you'll go back where you started today, right? So let's see here. So, or maybe you'll go someplace else. I don't know. It's up to you, I guess. So this is I. Well, let me write over here. IP. All right. Because the term in front is the integrating factor again, right? Okay, so step 2 is to multiply star by I. That gives me I dy dx plus IP y equals to IQ. Right. Let's do it for my parallel running example. Step 2, multiply. We get x squared dy dx plus 2xy equals to x squared over x to the 4th, also known as 1 over x squared. We divided by y, and we lost the y equals 0 solution earlier today, right? I just multiplied an equation by an object. You might worry, if that object is 0, we could be modifying the solution set, right? But look at this integrating factor. Is there any danger of it being 0? No, I mean, it's the exponential of an integral. right? So long as p is at least piecewise continuous, as long as the integral of p exists, the integrating factor exists, it's an exponential of something, so it's a positive thing, right? So it can't be 0. It's harmless, this multiplication by integrating factor of the exponential of blah, blah, blah. All right? So why do it? Well, that's step 3. Step 3, if you look here, this is d dx of what? If you look over here, this is d dx of I times y. Product rule, right? So when I take the derivative of I times y, I get I times dy dx plus the derivative of I, which is, by the way, IP, right? Times y again. So this is the product rule in reverse. All right, product rule in reverse. If we have calculated the integrating factor correctly, the product rule in reverse will be apparent. It will be manifest. That's the case here, right? This is the derivative of what? X, right? Yeah, x squared y, right? X squared is the integrating factor, y is the function. That has to happen if you have executed the method correctly. There's a built-in quality check here. If you calculate the integral, constructing the integrating factor wrong, this won't work, right? So don't just go through the motions and write it down assuming it's going to happen. Actually check it. You have a redundancy in this calculation. It's wonderful. And then step 4. At this point we have the derivative of something is equal to something else, right? So we can integrate both sides to get I times y is equal to the integral of iq dx. Therefore, y is equal to 1 over the integrating factor, the integral of iq dx. So here you go. That's a general formula that solves an arbitrary first-order linear differential equation. Assuming p and q are nice enough to integrate, right? But that's not a very strong assumption. And then, of course, over here, for my example, we get that x squared y is equal to minus 1 over x plus a constant, because we can actually do the integral, right? Integrating both sides. Right. And then finally, since I'm looking for an explicit solution, I never told you that, did I? I should have. Right, let's find an explicit solution. So 5 to find explicit solution. Solve for y. Be careful. You gotta know your algebra. So that's minus 1 over x plus a constant all divided by x squared, right? Which simplifies to what? Minus 1 over x cubed plus a constant over x squared. Now, we do teach this in Calculus 2 most semesters, right? So if you had Calculus 2 here, you probably saw it. If you had Calculus 2 somewhere else, odds are against you of seeing it, I think. I mean, I don't think everybody teaches this in Calc 2. It is in the book, you know, but I have a suspicion there exist universities where this is not taught in Calc 2. Do you guys remember this at all? Somebody? Vaguely? It's not something you do all the time, right? So, I mean, it's easy enough to forget. Let me find my examples here. So my example 2.22 is kind of more or less that same example. My example 2.23 on page 19 is probably good to look at. here I say let r be real constant. And what I want to do, and g some continuous function, all right, we want to try to solve dy dx minus ry equals to g. So a lot of problems, a lot of applied problems basically come down to, oh, I'm sorry, not an x. Let's make that x a t as well. Okay, let's make that x a t. So this problem, right, g is going to be part of the answer because g is kind of arbitrary, right? R is going to be part of the answer because R is arbitrary, but it's a real number, right? But we can apply this technique to solve this general class of problems. This is, so is this in, it's in the right form, right? We've got the derivative plus y times something equals to the other thing. So can you identify? So this is a linear differential equation in standard form. I think the first order of business whenever I do one of these problems is to identify, say, okay, it's linear ODE with P equals to what? Minus R, right? And Q equals to G. The independent variable is what? Is T. So what happened with X in the previous problem should happen with T here. All right? But we follow the same procedure. So like step number 1, integrating factor is what? Exponential of the integral of P, which in this case is minus R. Instead of putting dx, I put dt, right? We should all be able to do this integral, right? It's the integral of a constant times time. Just the, right, just, so this is the exponential of minus RT, right? Or as you might usually write it, e to the minus RT, right? This notation, exp, I just use that when I want to make the argument of the exponential bigger, right? Okay. So step number 2 is what? Multiply the differential equation by the integrating factor. So we have e to the minus RT, dy dt, minus r e to the minus RT, y equals to g e to the minus RT. Now, if things worked out, what should we see at this point? We ought to be able to see the reverse product rule, right? So, let's see here, this ddt of what? You guys know? Someone here knows. Come on. Yeah. Yes. Right. So there you go. And now we integrate both sides again, right? Integrating gives me that e to the minus RT times y is equal to the integral of g e to the minus RT dt, right? So therefore, y is equal to e to the rt times the integral of g e to the minus rt dt. And that, folks, is as good as we can do. I mean, all we can do here is to find what's called an integral solution, right? So this is an integral solution. In other words, it's a solution which involves an integral. If you want the really antiquated terminology, people used to say it's been solved up to quadrature or something, which is, you know, it's a useful thing, because if you actually have a specific g, there are many techniques known to calculate the integral of something. So this is actually very useful. Now, if we put g equal to various things, we can get different answers here, right? This is an answer of answers. This is like a meta answer. Like, for example, what would be something fun to put? What if we put g equal to, I don't know, how about put g equal to e to the rt? What happens then? These, you have e to the rt, e to the minus rt gives you e to the 0. This integrates to give us t, right? Plus a constant. So y equals to e to the rt times t plus a constant. So like there's one solution, right? What would happen if we had g equal to e to the st, where s is not equal to r? We get 1 over s minus r e to the s minus r times t plus a constant. Because if we have e to the st there, then e to the st times e to the minus rt is e to the s minus r times t, and when we integrate, integration brings a 1 over s minus r factor, right? Which makes sense, provided s is not equal to r, we can do that integration there. This example is actually kind of interesting if you look back at it later this week in view of our later techniques. Okay? But anyway, so that's the integrating factor technique. You know, you need to work like 5 to 10 of these at least before you really get up to speed on it, right? So my advice to you would be go work all the recommended homework problems until you're like, I tell students until they're bored with it, but Dr. Smith has warned me that that is incorrect. Because you might be bored with it at the start. It's like, man, I don't want to live in that world. He says you should do examples until it hurts, and then do 2 more is his advice. So I don't know. I guess this is advice that's born of actually going to the gym or something. I don't know, but whatever. Here, so that's the integrating factor technique, which is awesome and useful. That brings us to our next method, exact equations. All right. The integrating factor technique, it's pretty obvious when you need to use it, right? I mean, you can kind of see when an equation's linear. It kind of sticks out. You know, the one thing here that really requires a lot of thinking probably is the substitutions. When a substitution is required, sometimes those are kind of, there's a lot of different flavor choices there, admittedly. But we'll get to that eventually, maybe tomorrow. I forget when we finish today, so I don't know, but let's see here. All right, so exact equations. This is probably, I really think it's simple, but I have a lot of trouble getting students on the same page. Basically, the thing is this. In Calculus 3, we learned if you have the solution set to this, what is it called? Level curve, right? So the solution set of a function of 2 variables equal to a constant is a level curve. Many examples exist. I don't know what example I'm on at this point. 2, 2, 3. Oh, man. Let's just call it example 10. I probably missed a couple of examples, but you guys will deal, right? So example 10. So if I had, for example, x squared plus y squared equals to 1, right? I mean, oh heck, you can make this r squared. Same song and dance. These are circles, right? If you take the total differential of this, what do you get? You get that, right? So if we have a level curve, we can take the total differential, and that shows you how the change in x and the change in y is related for a level curve, right? If you want to find out what dy dx is for the level curve, solve for dy dx, right? And that will sometimes make sense, at least in as much that, as much as y, provided y can be a function of x at the point in question, then this will make sense. Of course, you're missing something. You're missing those points with vertical tangents. But a level curve, you can calculate the differential. If you solve for dy dx, that shows you the slope of the solution, right? At that point. Again, assuming it's not a vertical tangent. Another example. If I had x squared minus y squared equal to some constant, right? Take the total differential. And so that differential equation, I mean, this level curve, the set of level curves, of course, these are hyperbolas, right? Or if you put k equal to 0, they're the lines y equals plus or minus x to the origin. But this level curve is, in fact, a solution to dy dx equal to what? We've got 2x over 2y. Basically, the idea is this. We're dealing with an exact differential equation if I can recover the solution to the differential equation in this fashion. Let me write that down a little bit more carefully. M dx plus n dy equal to 0 is an exact differential equation if there exists f such that partial f partial x equals to m and partial f partial y equals to n, all right? If m dx plus n dy equals to 0 is exact, then f of x comma y equals to a constant describes its implicit solutions. So this is a theorem. Here, of course, I'm saying m is partial f partial x, n is partial f partial y. I'm using the same, talking about the same f. Not every differential equation is exact, right? All right, so let's see here. How do you solve,